lectures.
Yeah.
2 lectures.
Yeah. So
Can
let's
we
start.
turn on the AC first or something? Is it any hot in here?
You have to turn this one on,
Which
right?
one?
Isn't it connected to there? Yeah, is there a
We didn't
switch?
have AC during your class. Yeah, we didn't have AC. I don't think it works.
No.
Oh, it works.
No, it's working. Okay. Cool.
Yeah.
All right. So let's try to understand how to use path integrals in quantum mechanics. So the basic problem in quantum mechanics is this, right? You want to find the wave function at time t. The way you do it is just use the time evolution operator and initial state that we call it psi of t. And if you have a system with a time independent Hamiltonian, the time evolution operator is nothing but e to the minus I, right? And the typical example of a Hamiltonian would be squared and P and Q are the canonically conjugate variables that obey this. So we have become adults now. So we say h bar to 1. But you might ask, why are we not setting? Why are we not, omitting the hats? The idea of the hat is to illustrate a point later on, so I'm just going to keep the hats for now. Now let's say if I want to express this in coordinate basis. So what do? I just take a coordinate basis and just act it on this equation. So what I get is this. If I add q, this guy, I get the wave function, that's this sine 2p, that's just q. Now if I want to express things in terms of the wave function, I better have the wave function on the right hand side. So how do I get the wave function on the right hand side?
I forgot. So we have a form of the Hamiltonian. So
Yeah.
my recommendation is we put the form in for H
Yeah,
and then insert an identity with a momentum basis
Yeah.
to evaluate operators.
I'm
on
gonna
the
make use of the second part of the answer. I'm gonna insert an identity here, which is nothing but K prime Q Q prime Q. Right? Now this thing I can call sine Q prime of T naught, wave function, and this thing is called the propagator. And let's denote it by A. So, just to review, we are starting off with quantum mechanics. In quantum mechanics, we want to find the wave function at time t. We do that by using the time evolution operator, and it's typically this thing. If you want to express that in the position basis, you act it on the position get. What you get is this is a wave function, and I insert an identity here. And then I call this guy the wave function at initial time t naught. This is called the propagator. And once you have the propagator and the initial wave function, you can find the wave function at any point in time. Now there are several ways to evaluate this thing. We are going to look at Feynman's way of evaluating using parameters. So that's the next thing to do. We want to evaluate this. can be written in another form as well, which is this. We agree on that? This is just Schrodinger to Heisenberg fixation. So, by definition, we have plus. Why is it plus and not minus? You know, we wrote the time evolution of a state with e to the minus, right? Why are we writing the time evolution of the position state with the plus?
Which one is the Heisenberg picture and which one is the Schrodinger?
This is Heisenberg. Sure. Wait, the other. This is Heisenberg.
Yeah, I'm right.
Independent.
This is Heisenberg
Yeah,
and it's Schrodinger.
yeah. And why is it plus either? What's that? This is minus, right? So we write the time evolution like this. With the minus. Why are we writing the time evolution of position with the plus? This is also
I have a guess.
yeah.
Because I think to convert between the pictures, we need to have a unitary operator in between, or sandwich whatever it is in between. And so I think maybe this is the one of the unitary operators. That's my guess.
So I'll give you this.
The kind
Idea-
of plus or minus is still there, right?
But
Yeah.
what is it then?
Do I
Give the answer.
No, I forget. Unitary does not include complex conjugation.
It does.
I'm just saying that
I
either
don't
way,
mind.
if it is minus in the exponent or plus,
It's
there's
still
still in the exponent.
Uh,
Right?
So the reason is simple. In Schrodinger picture, you evolve the states, and the way you evolve the state is like this. In the Heisenberg picture, you keep the states the same, but evolve an operator. The way you evolve an operator is this. That's right.
I'm trying to figure it out.
It's either this or the other way. But anyway, in the case,
It is this way, I think.
position is an operator, right? So in the,
Yeah,
the
it is.
Heisenberg picture, you
Yes.
instead of changing the position vector from this to that, you change the position operator. So when you change the position operator, the basis vectors has to change. It has to change exactly in the opposite way to make sure that everything works out. Is that clear?
I think it's gonna be clearer if you calculate like the expectation value of some operator.
Right. Let's do it. So let's find the position value. This is nothing but this, right? Let's say at time t. So I rewrite this as sine of 0 plus I. So in Heisenberg's picture, we say that these guys stay the same, but A evolves according to this equation. So every operator evolves according to this equation. So position is also an operator, right? We have Q hat. Q hat of T is nothing but IHC Q hat. And if the position operator is evolving, the eigenstates of position has to evolve. And that evolution is opposite.
I have a confusion regarding the definition. two instances,
Yeah.
D prime, D double prime.
Yeah.
So we will have two separate kits.
Right.
Q D prime, Q D double prime.
Yeah.
Right. That one, that doesn't that mean that kit had changed as time went on?
Now for demonstration,
That's what I'm trying to get.
So
How
what's
much
that?
do you use the smaller time
So
So
at this time,
Q
Yeah.
at this
Q
time, they may not be
They have to
same.
do your time.
And when we say that you
That's something.
write the other one as Q double prime D prime. You can just always see.
No.
The time change.
Yeah.
Can
Just
change.
you was.
Yeah.
What you
That
do.
we say that in Heisenberg's picture, state of the system should be the same. Does that mean
No,
that?
no, no. The entire dynamics of this thing is inside that. So it doesn't change. The kit doesn't change. The operator is. This is not a state vector. That's my point. This is a basis vector of some operator. It has to be because basically the operator is state. So I think, is that clear? I mean, it's not very important.
It's very confusing.
Yeah, forget about it.
I don't know. I have to remind myself every time I do like that.
Alright, so we want to find out this thing. So the way we do is the following. So let me simplify my life by denoting P minus Q as big T. So the propagator I'm trying to find is this Q prime 0. So the way to do it is you take time, which is from 0 to big T, and slice it into m plus 1 equal parts. This is part 1. And each of the segment has the length epsilon. Right? And now what I'm going to do is insert, again, that's the classic trick, an identity at every slice of time. So we get every instant slice of time from 1 to n. You don't have to insert in anywhere. That's okay. Is that clear what we just did? We just inserted a bunch of items. That's all we did. So this immediately gives us a physical picture for the whole process. So what does this mean? This is the probability amplitude of a particle by gross space-time diagram. It's a probability amplitude of the particle starting at q prime at time equal to 0. Let's say q prime 0, and then propagating it to q at time t.
Strictly, it's not a probability amplitude yet.
It is.
Such a modulus squared is probability amplitude.
That's probability.
probability.
This is
Oh my
probability.
god.
amplitude.
Yeah.
So what we just did is we sliced time into a bunch of pieces, and then now look at each of these pieces. This is the probability amplitude of the thing going from this position to that position, right? That means it's going from here somewhere here. Then in the next instant it goes from this to the next one, which is here to say here. And we are integrating over all of these guys. Q1, Q2, Q3, and all. So that gives us the physical picture of the city. It goes to that part, this part, that part, every part. Hence path integrals. Is that clear or? I feel like it's not clear.
So, is it, you're summing over all paths, right? But inside the integral, you simply have the product of those all amplitudes.
Yeah.
So, I understand the sum of the amplitudes. What is the product of amplitudes?
No, we are summing over all the intermediate positions. So these processes has to happen sequentially, one after the other.
I see the sequential amplitudes, right?
Yeah.
Q, Q, and that's one, Q, N, Q, N, T minus one, N minus one, right?
Yes.
But those are the individual amplitudes. They're in products.
Right. So it's just this. If you're tossing a coin, for example, what's the probability of getting head and head?
Oh, I see.
It's 1 by 2 times 1 by 2. But in quantum mechanics, you don't multiply or add probabilities. You add and multiply probability amplitudes.
I see. So you're basically, so when you let's take one of those amplitudes and you integrate over Q.
Yeah.
So for that particular time slice, you're integrating over all possible paths.
Yeah.
Right, and then take times it by the next time slice, integrate it over all possible paths in that slice, times it by.
Yeah. So the only places we are not integrating is the initial and the final. Yes.
Let's just focus on DQ1. So
Right.
that is for the first slice.
That is for the first class. Yes.
So that by integrating over that Q1, we take into account possibilities of the particle being any point.
Yeah. So there's this question of, does it violate relativity and all that? That's irrelevant because this is not something that you can observe or anything. This is just a trick that you use to compute. So as long as the final results are consistent with relativity. Okay.
Yeah, but I will do what Sujit was suggesting. If I'm still confused, I will consider just a single cut and then take this interpretation. Like the particle can go, let's suppose, in a straight line from here and then to the end point, or it can go to any point in the middle cut that you made. And then I add another layer, and then I add another layer, and then another layer, up until the point you're comfortable with seeing that forms any sort of in any shape of path, not only like straight line here, straight line there. If you add a bunch of straight lines very close together, then you can get curves, right? That's the whole notion.
So technically, for it to be a path integral, you have to take like a limit. Of
Yeah,
the
we're
n,
going
right?
to take the epsilon going to 0.
Yeah.
He's taking the limit as physicists, right? Epsilon. Every time epsilon
Epsilon is
is
already
like
small.
infinitesimal.
I'm going to use that right now.
Sometimes epsilon is energy.
Not in my book. Where? In Landau?
Yeah.
Just don't read Landau. No, I'm kidding. Oh, he's recording.
So you might think, why did we just do this gymnastics? That will be clear right now. Let's take a look at one of such terms. Let's take J. Minus 1. This can be rewritten like this, right? Q J. What's the kind of period?
Epsilon.
Epsilon. That's okay. Is that okay?
Ooh.
Right. Now, what is this term? Just e square by 2n plus q epsilon, right? It would have been nice if we could split this into e to the p squared times e to the vq, then we can add e to the vq on this guy and get the eigenvalues. But there is this rule that tells you that you should do that. E to the a plus b is not e to the a times e to the b. Yeah, PCH. But I'm going to do that nonetheless.
That's illegal.
And we did do something with something. We did this with that. Both comes with an epsilon, right? So there is
So you throw it away.
right? So I'm going to just throw it. I'm going to set this guy
And what is option?
epsilon.
Epsilon small. That's it. Always.
I see.
Epsilon squared is small.
Do we need to do this? I don't think we need to do this.
I think this is the easiest way to do it. You can tailor expand it and do it.
No, I'm just saying, like, if we insert, are you gonna insert the momentum
Yeah.
basis
Yeah.
identity? If we insert it to the left of the exponential, we just have to require that whenever p and q's appears in the same term in the Hamiltonian, the p's are always to the left of the q's.
Yeah, but when you exponentiate this, you will have those. How do you deal with that? Say for example, take p squared
That
plus
is true. That is true.
What is the last?
That's true, yeah, we have to use it anyway.
What's the last one we called this?
oh
Yeah.
so you have this identity, right? E to the a plus b. E to the a, e to the b, e to the commutator a b, and some number here. Right? So here a is p squared by 2m times I times epsilon. Right? B is VQ times algebra. And then we did to the commutator, you have an epsilon squared, which I set to 0. Because it's small. So
That's true, we have to break.
once we have that, you can just put that inside.
Oh.
Yeah.
Oh.
J I've acted on QJ with this guy because it's pretty good. Now I want to get rid of this operator as well. How would I do that? I just insert an identity with P. this to C, then just replace this by PG. Now these are just numbers, right? And what's this? Get they are numbers I can just combine them into one exponent. What are they?
Plain
Even something. So
KT.
this is just this. Plus or minus. It's plus or minus, it doesn't matter. Let me follow what I did.
I think it does matter.
Let me follow what I did.
But I forgot which sign this is.
So then this is minus, right? Because it's flipped. So overall I will have is that This 2 pi comes from 1 square root of 2 pi from this, 1 square root of 2 pi from that. And then this. It's okay, right? Now I can just massage it a little bit. I'll take an epsilon out and divide by an epsilon. What's this? Qj minus 1 by
The average.
it's the velocity.
Oh, yeah.
It's the consecutive positions difference divided by the time.
The x.
So I define it to be the velocity at Qj. So I have
velocity, the speed of it can change as it moves between the slices.
yeah.
To take that into account, we have integral over
dq.
d.
So we have integral over dq's, right? So these are integrated over. So velocities can be different. So we have this guy. And we just have to plug that into this, where every term is exactly the same. So
It's a bit weird because it's H, E, J, Q, J, but the potential is 2J minus 1.
what's that?
So you define the Hamiltonian,
Oh,
there's a EJ, QJ.
how do I make that? I can always make that right by hand.
I mean, it's probably something minor.
It's too much detail for nothing.
Yeah.
I think you can just keep J minus one there, and
Yeah.
then when you take the limit of
It even
QJ,
doesn't matter, yeah. J minus.
QJ minus one is basically
It
simple.
doesn't. Let's put that in this. I'm going to fancify the notation a little bit. Right, fine. J equals 1 to that's all of these guys. And now I have a lot of integrals over j's, right? And how many pj's do we have? So we need to insert a pj for every one of these terms. Right? There are, I have 5. Is that clear why there are n plus 1 terms? Because we split time into n plus 1. That's all, there's nothing into it.
So this one. Oh, okay.
Yeah, starting it from 0.
Oh, I did some just quick clarification. We divided time into n plus 1. N plus
Equally.
1 slices,
Yeah.
which means there are n delta q's.
No, n plus 1 delta. That's all.
They're just n delta q's. N plus 1 dp's.
That's my question.
How many have the sample is 0? N plus 1. It's this. Coming. Right. Now let's put those guys in. So I will have that is a minus sign somewhere. No, yeah, I have this kind of term for everything right now. For qn minus 1, q la 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 la, with everything. So I have some is that okay?
Isn't it L equals 0 for him? Just like it. And also, oh no.
No.
No, I think, yeah.
The 0th one is the thing that we hold fixed.
No, yeah, so you're inserting n plus 1 p's, right? And the way it's written, there's no presence of p0 at all.
Yeah, there is no presence.
So why?
Yeah, this is fucked up. This notation I messed up.
No, I think you're supposed to. Oh, okay.
I mean, it doesn't matter. That's the point.
When you take the limit, it won't matter.
Yeah.
And again, I mean, the q should be.
I may have messed
So
up
L
thinking
minus
this is
1.
somewhere, but
Yeah.
it's actually relevant. Now I'm going to take this limit, epsilon going to 0. In that limit, I fancify the notation. This.
Okay.
So epsilon times this summation becomes integral of dt. Because epsilon is time slices, and I'm summing this thing for every time slice, which is just an integral. So it's I integral 0 t questions.
I need more of a picture. I don't know why I'm so bad at this, but slicing the thing up into what n slices. And maybe you can draw me another diagram. Yeah, so is that reflected here? So I divided into n slices. I have
It's n or n plus 1 should matter.
Think about it, like in the beginning you have one slice, right? Every time you add a drop,
Yeah.
you add one slice.
yeah.
So if I added n drops, I added n slices, right? But in the beginning I already had one, so it's n plus one. So if you divide it by n drops, you get n plus one slice. Because you added n more and you already had one.
Let's see, let's take this.
I'll
So
strongly
why is it-
recommend you to do the calculation for just one slice.
Yeah.
Just do one slice.
Why is it from k equals 1 to n plus 1 for pk?
There are n plus 1 integrals for PK. So we just want to introduce n plus 1 p integrals, that's all I can do.
Dima, if there was just one DQ there, forget about DQ2 for the rest,
Yeah.
alright? How many inner products that will be integrated, will be integrated?
Just one. No?
Count again, because we inserted one identity,
Right.
and we already had one inner product.
Oh, that's right. We start with an inner product.
So we have two.
P is one extra. That brings me to a question Sujit asked me yesterday. So, what's the dimension of P?
What?
I mean, in this integral products, right? We have say n q's and n plus 1 p's.
It's a big dimension of one.
Q times p has the dimension of h bar,
Which,
its angular momentum. So Q times p doesn't have any dimensions. So this overall has a dimension of p, which is just 1 over length. Is that consistent?
You go with that again, so P
Yeah.
times Q has a dimension of h bar.
Yeah.
So,
And we have set h bar to 1, right? So PQ has no dimensions. But we have n q's here, n plus 1 p's. So there is an extra p. Is that consistent?
Yeah, because you're in that's a kernel.
Yeah.
So the answer is just this. We had this, right? Sin x p is integral
Yes.
dq prime k
So-
psi q prime p naught or something like that. And the dimensions of psi and psi cancel. So k must have the dimensions of 1 over length. So this extra p saves the day. Right? P has the dimensions of 1 over length. Because PQ has no dimensions. So P is 1 over length. Right.
so everything works.
Everything works out. Now let's specialize to the case when Hamiltonian is just quadratic. If Hamiltonian, so we have this formula, right? We have this is approximately equal to the saddle point formula. You remember how to derive this?
No.
It's simple. So you
Expand F.
write fx x naught and you look at saddle points. At the saddle point, you look at stationary points. This f prime is 0. So then what you have on top of the exponential is some constant times your Gaussian. Gaussian gives you the square root of blah blah blah. I missed it. And did I miss it? Or miss it? So, and the extra phase is this, right? But if f of x is just quadratic, this formula is exact. Do we agree on that?
Yes.
Otherwise, it's left as an exercise. It's simple. Just find it in both ways. Find it using the formula and
I mean, the higher order derivative will just be zero.
just be zero anyway.
That's
So it's just clear from that.
That's
So-
the-
If
But you say it's gonna be zero, so it's.
the higher order derivatives, they're going to be zero, right? If it's quadratic.
If it is quadratic.
Yeah.
Okay, yeah.
right,
Yeah.
so
I thought you were talking about like.
If the
it's
Hamiltonian is-
not quadratic.
quadratic, then what's on top of the exponential is at most quadratic. If this is quadratic, we have a linear term here. This is quadratic. So how do we find the result? We just do the same thing. We first find the extremum. How do we find the extremum? 0 is divide p. What's there on top of the Hamiltonian, which is nothing but p q dot h, right? Or in other words, this gives q dot h v and solve p from this, right? That's what we did here. We found the extremum. X naught is nothing but this. X naught is given by that. So we do the same thing. This is some function of p. We find p naught by extremizing it. So that's the solution for this equation. Solution for p from this equation. And then we substitute that back this. What is that process? In classical mechanics, we've seen this. It's just going from Hamiltonian to Lagrangian. Do you remember how we went from Lagrangians to Hamiltonians? Right? So what do we do? First we find q dot in terms of p from this. Then we substitute that. It's the opposite.
Yeah,
We
but-
find p from this and substitute this. So in the case of quadratic Hamiltonian, I mean, once we do that, then the dp integral is easy. It's just some constant times e to the f of that thing. So we are left with this. The dp integral is taken care of. When we do a dp integral, we get some square root of blah 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 blah. That I'm going to absorb into this dq. I'm not going to write that in this. And then this is exponential. That
What was the motivation for extremizing with respect to the
oh, just this thing. So we have this formula, right?
Right.
So this is exact when f of x is quadratic. So how do you find the right hand side of it? We need x naught. X naught is given by f prime of x naught is 0.
And our normal video is quadratic.
Yeah, so we want to find the extremum of the entire thing, this thing, for p. So this is how we do it. this is the classic expression. And we have also Q is
Does the font set not matter?
does it?
Isn't that considered the A that Jen had,
Yeah.
that A sticking out? Right? That's the concept.
So I'll tell you why the constant doesn't matter in 5 to 10 minutes. Now let's try to look at some generalizations. So if we want to find this first. How would we find this?
Time slice again.
Yeah, you do exactly the same thing. Time slice again, insert identities and all that. But when you insert identities, there will be one identity which is integral of Q. I mean, you will have, when you insert identities, you will have one like this. Right?
We should place the operator in some special response.
Exactly. So this operator can hit on this guy and give you a number. Then the rest of the process is exactly the same and you'll end up with this. Is that clear enough?
So it's the point that every operator that's like a function of P and Q gets turned into some
Number.
number.
Yeah. These are all numbers. There are no operators in this. But that was the point why I wanted to put the hats. These are operators. These are numbers.
See.
QFT over. Okay. That's the position evaluated at a particular time.
Yeah. Now what if I look at this expression? What would be that?
It's just
So
big
it's the
Q.
same thing, you time slice the entire thing again and you have to replace these guys by operators in between, right? So if T1 is larger than T2, then you have to place this guy to the left. Because remember we had this. Something like that, with integrations, which I'm omitting right now. So if I insert a Q hat of T1, it has to be, if T1 is more than T2, it has to be to the left, right? Let's look at this. Time goes slow, time becomes smaller and smaller to the right. Right?
Past is in the right, future is in the left.
Right, right. This is future, this is past, this is even more.
Right, but that's just a label, right? That's just the index on the time space.
Yeah,
It doesn't say
but
how big the interval or small the
no, it's not about the interval. This thing relative to T slicing the time interval from each prime to big T into pieces, right? This is T1, this is Tn. So Tn is larger than T1.
Yeah.
It's all related to T prime.
Okay.
So when you go to the right, the time values are getting smaller and smaller. So if I insert two such numbers, if I want to make them into operators, if T1 is more than T2, Q hat comes on the left. Q hat T1 comes on the left. Because T1 is more than T2.
So you the time ordering operator.
Yeah, if T2 is more than T1, then Q hat of T2 comes to the left. Because obviously that's how the time is arranged in this problem. So we get this. This is a time ordering symbol. Doesn't really just says that whichever has the largest time comes to the left. That's all. Is that clear? It's pretty clear to me. I'm just asking. Is that clear to you?
I don't. Can you? Sorry, man. Q hat T1 will
Yeah.
only see Q1 T1.
Yeah.
So I don't actually. Maybe I'm totally blind, but I really cannot see why the order actually will matter, because they only see their respective ket sticked and hit that.
True. But you see,
I think you start on the right hand side, go the other way.
What if you had written it the other way around, right? That's good.
inside here,
Yeah.
you
No.
can change the labels, but the time here is
Maybe I think it becomes clear when you start from the right hand side of that equation
and you can start from here and go.
and do the same thing that Robin did a while ago.
Insert identities in between.
Dima.
Yeah.
So you're claiming that probably, I mean, you don't see why we need this time ordering operator, right? In your opinion, we could have written like QT1 or QT2 either way, right?
Yeah, I think so.
But that's, I mean, without going through the math, we can see that that's inconsistent. Because whatever is in the left-hand side, inside the path integral, QT1 and QT2 are just two variables, just numbers, right? They clearly commute, right?
Right.
But what is inside the inner product are two operators. They do not commute
Because they are operators at different times.
I agree with that.
unless you add some type of special operation that makes them effectively commute.
Now they commute, I can write T of QT1, QT2 or QT2, QT1, does it matter?
Because the order is set by the time ordering operation.
I think somehow they did go that.
So I'm not claiming that this
No.
proves that we need
It's just
specifically
violations.
the time ordering operator, but we need some type of operation that orders the operators in the right hand side of the equation, right?
I think maybe it's hard for me to see immediately that why would T2 be less than T1 ever? I
Because
know.
those are just variables.
Yeah, I agree.
Separate.
But I mean,
Yeah, like this.
They are two random time labels.
T1 or
First
T
one
down.
was first, and second one was. I don't know.
Yeah, if T bar is more than T bar bar,
So the closer to the initial time goes to the right, right?
Two of
Yeah.
them should
The time goes to the right.
yeah,
I mean, that is actually, I think the
So-
idea isn't about correlation of it.
So
About the two position operator.
what if we want to calculate something that we sandwich Q bar T1, Q bar T2, but T1 is less than T2? Is that something we can calculate?
which is particularity.
Can't you just use the, do you know the commutation relation between the two?
No.
We know the computation.
I mean, then it's hard to do anything, but assuming that you know permutation list, and then you can do stuff.
Let's say
Yeah.
But why
Fortunately, everything that we're needing, QFT
is
comes
sometimes
with this high model. Maybe that's just coincidence indeed.
you can formulate QFT without time ordering. That's pretty hard. I think Peter Arnold does something like that. He told me I didn't understand.
Also,
if you want it
I
the other
just
way,
never heard of it.
also hyperverse, eventually they'll line up. And I said that doesn't seem to me why we would introduce a time order at all. Since it will eventually line up. Man, can I ask you to do an example? Do slice time into, just evaluate Q hat T2. No, you evaluate inner product of Q T1 and Q T2. And assume T2 is greater than T1. I can't do it. I can't. I'm in count that's sorry, why am I not seeing this at all? Let's just pretend this. So here's Q, here's T, and I want to do this.
But why is that?
Okay. I do this. Let me just do something stupid.
So I guess this has to be information.
Yeah.
Okay.
This guy will only
So what about-
see this, right?
Now here's the real question. What if there's 3 operators then? No, what if
So,
there's 4
okay, so
operators
are
there?
you saying that this
It's
guy
not in like reverse
cannot be
order?
brought to this identity?
This guy will only see that. That's true.
Yeah, so it will just become a C number without.
Yeah, but it has to be.
How do you recombine later, Timo?
Yeah.
That's the issue. Because to go through the procedure, we had to insert the identities such that we go from like higher time to lower time, like to later to earlier in time, in a sequence, right? If you do this with Q1 being
Oh, I see.
with respect to a time that happens before Q2, then you're messing up the order.
Oh, I see. So let me think about this one then. Let's do it properly. Okay, now so this will evaluate. Okay, I think it's making sense. If I suppose maybe for some reason T2 is earlier than T1, then this ordering won't make sense.
Yeah, you have to hold it together.
Okay, that actually does make sense, I guess. But if T2, but if T1 is earlier than T2,
It's actually not as trivial as I thought it would be.
You have to think about this, but it's not, it's still coming.
Because
Just start from this. That's
Yeah.
that's all you.
yeah, but now that I think about it, what if you do so at the start of your lecture, you instead of inserting the identity operator for a time that's in the future of the initial state, what if you insert it in the past?
Then this whole derivation will go through.
Yeah, but is that not allowed?
So in that case, what you would have is something else, and these are not infinitesimally close to each other. Then you cannot do the Baker Campbell trick that we do.
Why not? Sorry.
Because we neglected this term, right?
No, but if we insert it in the reverse order, but infinitesimally,
Yeah, it would work, right?
it wouldn't work because
Initial and final. So there are 2 terms at least for which that would not be. Because there is a final state and there is the initial state.
right.
The inner product of the final state, if it's closer to the initial time identity, that will cannot be used.
we are taking the product of the final state with the first time slice. So that's not right.
I'm trying to
You need
understand
to
Josh's
take the
question.
final state with the
Yeah, nice.
time slide right next to it.
Josh,
Mhm.
I'm trying to understand your question. You're saying, what if we insert, this is how time goes? One and two. What if we inserted, an identity in this time before, to the left of this?
Even at the start, just to make it simple. Just to
Oh
make
yeah,
it,
that's one of the, so, like, we had this to start, right? T, Q, 0. And then you wanna insert, like, this first, Q1, Q2,
so just insert one,
Just insert one? Okay. Okay.
Now T1 is less than 0.
Okay, how would you evaluate this? Every variable is
We're
like,
just doing math here. Why do we evaluate anything?
hmm?
What do you mean, how do you evaluate?
Oh, shouldn't we have like just a single epsilon in the middle? Because when you change this to Schrödinger picture, this is you. Time, which I'm leaving as blank.
Ah, I see.
Q1. But now it's not infinitesimally close to the, that's what I'm saying. You
If
just
it's not
into,
infinitesimally close, then you cannot do this.
Okay, I get it.
in the end, you'll have some trouble recombining this, like taking the limit to the continuous phase.
I'm sorry about that.
Thanks.
No, that's it's good that you.
Alright,
So in QFT, it turns out that we need to evaluate stuff with time ordering.
Michael, I had a question.
Yeah.
I didn't even need to find expectation value of 2 Qs.
That will be answered a few weeks later. That comes because of this thing, which is yet to be derived.
So far. That's amazing.
And this is computed via inserting just numbers in the math interface. So to do this very efficiently, we introduce sources. So we change x to h minus f cubed, p qt, now we evaluate q, p, q prime, p prime is the same thing that we evaluated in the presence of these f and h.
So just take the derivatives.
Yeah, this would be nothing but, I mean, I'm not doing anything new, just changing.
But inserting those additional terms, doesn't that change, do anything with the, what is the impact of the sources on the action?
Yeah, we are changing the action, but oops, it's 1 hour, so should we stop?
how many more lines?
Two more boards.
5 minutes. Yeah.
Okay.
Two more boards.
So, yeah, I'm just changing this to P to this rule. This is just a definition. This is sort of continuous generalization of this. Now, if I have that, then how do I find Q? E, Q. Hang on. E1. So if I call this guy Z of F and H, right? I need to bring down at Q at T1 and at Q at T2. Right, this is nothing but this way.
Is that the new age?
Hmm?
The new age? Or is that the old age without the F, Qs and H?
Yeah, this is just the old age.
Okay.
So how do I get this from this? So I just take. Should I write it somewhere else? Try to find this. So if I take a derivative, the z thing, that is this thing with T1, right? What do I get? So I get the exponential like this, and you take the derivative of whatever that's inside the exponential. And when you differentiate f of t with f of t1, I get a delta function, which when integrated over will give q of t1, right? Same for q of t2. And in the end I can just set f and x to 0 to get. Is that clear, or should I explicitly do it? I'll explicitly do it. Let's say I want to find this. Right? I claim that this is nothing but
That's your Z is your generating function.
yeah. So let's just find this. So of you take a derivative of this thing. So that thing. Let me just forget the. Let me just do it for the Lagrangian version. Right? What's this? I want to write the Q by d of exponential is the exponential itself. E to the I ft. And then the derivative of the thing what's on top of an exponential. That's nothing but I integral dt d by f n1 right? And d L dft1 is 0,
What brings the whole integral down?
right? So this part is 0.
Right.
And d dft1 on that guy times definition delta of t minus t1. So when I put a delta of t minus t1 inside the integral, I just get the q of t1. And then in the end I set f to 0, which will give me precisely this.
Derivative of q of t with respect to f of t is 0.
Yeah. I said here.
We use this notation question. So the delta, is that specially used for just for differentiations for functional thing?
Yeah.
But the roots are exactly the same.
This is the only rule that we do. And it obeys the product rule, all that. So alright, so maybe we can start.
Time to take a break.
That's-